supposed to be talking already?
No,
Okay,
we're just
good.
waiting for the stream.
Now we are live.
Thank you. Welcome everyone to today's seminar. It's a pleasure to introduce Laura Salles, who is an associate professor in the Department of Physics and Astronomy at the University of California, Riverside in the United States. Laura obtained her PhD at the National University of Cordoba, Argentina in 2007, and then moved to postdoctoral positions in Europe at the Kapteyn Institute in Groningen, the Netherlands, and at the Max Planck Institute for Astrophysics in Munich, Germany. In 2013, she moved to Boston as an ITC fellow in Harvard University before joining University of California, Riverside as a faculty in 2015. Since then, she's been awarded the Hellman Fellowship in 2017, given to junior faculty with potential for great distinction in the area of expertise, and the NSF Career Grant in 2019 to study dwarf galaxies. Her main research interests include galaxy formation, dark matter, and cosmology. Her group uses and develops numerical simulation codes to learn about the physics behind these topics. Their projects involve the study of dynamics, hydrodynamics of the gas, and radiation from stars in galaxies. Thank you so much, Laura, for accepting our invitation. You may start when you're ready.
Thanks, Anna. Let me put some time tracking over here. It is my pleasure to talk to you guys today. Thanks for the invitation. Thank you, Anna, for this opportunity to talk to you today. Of course, it just feels closer to home. I'm originally from Argentina, from Cordoba, and because of the pandemic, I haven't been over there for at least 2 years. So it's getting long, and I'm hoping everyone in Latin America stays safe and improve soon so we can start traveling again. So today, I want to tell you some of our results on constraining the amount of dark matter in dwarf galaxies. Sorry. Okay, here it is. A very brief introduction of what I mean by dwarf galaxies. Of course, dwarfs is a very wide range and is used for describing a big set or heterogeneous set of objects, some of which I am showing in this picture. So M33, for example, a triangulum in the local group, one of them, this bulgeless, beautiful, perfect disk galaxy with a mass of almost 3 times 10 to the 9 solar masses. Is one example of a dwarf galaxy, not too dissimilar from the LMC, also in the southern hemisphere. I guess you guys have had the opportunity to see it. It's visible from Cordoba, where I am, so I suspect you might have a glimpse of it too. So the LMC is also a few times 10 to the 9 in stars, and is also referred to as a dwarf halo or a dwarf galaxy in this talk. But dwarfs can go all the way down to much fainter luminosities. And for example, you have over here in the bottom a picture of Seaway 2. And I'm saying picture because you can not really see it, except if the stars that belong to it, confirmed spectroscopically, have been highlighted here with these boxes. So these dwarfs can go then anytime from a few times 10 to the 9 to, say, 1,000 solar masses in mass. And even though to the eye, they become more attractive, if you want, as you climb up this ladder, the more massive, they're kind of more nicely looking. From the perspective of cosmology, they are more attractive the other way around. And that is because as we go down in luminosity, the prediction of cold dark matter is that objects become more and more dark matter dominated, which means then dwarf galaxies offer you the opportunity to study the physics of dark matter. But of course, we don't understand very well this mapping between the stars and the dark matter halos in galaxies. So what we can do is this exercise that is called abundance matching, in which you observe a given luminosity function that tells you how many galaxies of a given mass or luminosity is there in the universe. And then you can match that with dark matter halos in simulations. And if you ask with simple ansatz that the most massive galaxies are going to be living in the most massive halo, we can now establish a relation. And that the result of such exercise is shown here. In the horizontal axis, you have the virial mass, M200, so the mass of the halo, dark matter mostly. And then in the vertical axis, you have the stellar mass. Here says the galactic mass. And so what you find is that that mapping is really nonlinear. And it shows, so first of all, it's quite far away from all the baryons that should be there in the universe. So each halo should have this amount of baryons, but you see that the galaxies lie quite below this dashed line, which means galaxies are inefficient at forming stars. But that is particularly so for the low mass end and for the large mass end, or for the most massive galaxies. We have advanced quite a lot in our understanding of the shape of this function. And we now know that we do have different processes that can help us explain the deviation from this, say, one-on-one line. And so on the high mass end, we know that AGN feedback plays a very important role on stopping the formation of stars, and then therefore preventing those baryons to condensate into stars. And so this black curve gets flattened with respect to the extrapolation of this line. Now, of a bit more interest to our talk today is the low mass end. So for low mass galaxies, there is a larger set of physical processes that are important. Among them, we know that, for example, supernovae, or anything that has to be with the stellar evolution, is preventing the baryons from forming stars. And that is a combination of radiation from young stars, supernovae, and the combined effect of young stars driving outflows that you can see here in this image of M82, this red ionized gas escaping from the disks, right? So we know that stellar feedback plays a huge role on the low mass end. And the more we go towards lower mass objects, and I'm now talking an extrapolation downwards from where this vertical axis stops, we also believe that reionization is responsible for not only quenching star formation in many of the low mass halos, but also completely preventing any formation of stars in dark matter subhalos. So that is the price that we pay if we want to really reconcile the number of galaxies that we observe with the number of subhalos that cold dark matter predicts. Now, the issue is that our constraints on the luminosity functions kind of stop around 10 to the 8 solar masses, because we don't have sufficient completeness in large enough volumes to play this game of abundance matching. So therefore, all the talk of today will be trying to see or to push that limit downwards. So in other words, we want to understand for lower mass galaxies, or for any kind of dwarf mass over here, what exactly is their dark matter halo. And it turns out that if you use different tracers, for example, if you use the dwarfs in the Milky Way, like the velocity dispersion of the stars, for example, this is work by Mike Boyle-Colchin, you would get an idea that things are not massive enough to match what cold dark matter expects. And so the velocity dispersions are not high enough to see what we expect, but then you can also use rotation curves, as it worked by Ismael Ferrero in 2012, or a different abundance matching model. So truth is, whatever tracer you use over this region, because we don't have the luminosity functions complete, it gives you different answers. So what we want to make progress on today is understanding this mapping between stars and dark matter. And in order to do that, we will need to constrain two things: either the number of dwarf galaxies, sort of to extend the idea of the luminosity function, or to measure their inner dark matter content. So I will speak today about mostly two fronts in which we're doing this. The first one is focused on the local group, and more specifically on the Large Magellanic Cloud. This dwarf that I showed you at the beginning. It has about 10 to the 9 solar masses on stars, and is our most massive satellite in the Milky Way. So why is the LMC interesting? Well, let me show you this motivation comes actually from dark matter only simulations and by predictions of CDM. What you're seeing over here is a picture of the old Aquarius halos back in 2008. And this is a Milky Way. This is a halo over here, is halo Aquarius A. It's a Milky Way-like objects simulated with extreme high resolution. And so where the pink area ends is more or less the Vidiel radius. And what you see, well, of course, the typical characteristic substructure of cold dark matter, plenty of satellites within the Vidiel radius. But then if you really zoom in within each of these satellites, and here they're highlighted, I don't know, 6 of them, what you see is that each satellite that they are blow up here around the panel have their own population of satellites themselves. So one of the strongest predictions of cold dark matter is this hierarchy of a structure. So the galaxy has satellites, but then the satellites has their own satellites when they first come into the halo. And so this means that before say, if you take the LMC again as an example, the LMC should have come in to the Milky Way and brought in their own satellites. And you can make sort of predictions of how many satellites of which luminosity the LMC-like objects should bring. And this is shown over here. It's a work where we did like long time ago. And so this is the typical satellite luminosity function that we see for the Milky Way-like galaxy in black. And then it turns out that if your central is not really a Milky Way, but instead a dwarf galaxy, in this case, an LMC-like object, you expect, at least for whatever the model of this simulation was, that about, so this is the number of satellites above a given stellar mass. So each LMC-like object should bring at least one satellite of, 10 to the 7, so a Fornax-like. So the idea is then the LMC came in and brought in several of the dwarfs in the Milky Way. We know already of one, because this is a picture, of course, in the background. You can see the LMC over here. And this is the companion, this small Magellanic Cloud. And that one is one satellite, for example. And then the question is, which other dwarfs came with the LMC? Now, of course, studying the LMC is fantastic, but it has been processed by the environment of the Milky Way, and it's difficult to reconstruct which satellites came with the LMC. So it's work that we have done, and I can talk more about it, but the next step is to actually observe objects like the LMC, but in the field, objects that have not been tidally affected by, for example, the environment of the Milky Way. And once we do that, once we can actually survey these objects, then we have a way of testing the predictions of cold dark matter. Because if cold dark matter is correct, that means that LMC-like objects should have plenty of satellites around them. In particular, the more the faintest we can do these surveys. So we decided to study or to get better predictions for what is the satellite population of objects like the LMC in the field. So to do that, we used the FIRE simulations. This is work led by a grad student at UCR, Ethan Yan. So what we did is, and of course in collaboration with FIRE, and in particular with Andrew Wetzel, what you see here in the main panel in the top is an example of one M11 object, which means the virial mass is of the order of 10 to the 11, so about 10 times less massive than the Milky Way. And so on the right, you see the dark matter distribution. And again, you get the familiar plot of a lot of substructures. The red circle is the Vidiel radius. So it shows you that, as expected, Lambda CDM predicts a lot of these satellites within a halo like the LMC, or that we suspect the LMC is living in. And then on the left, you have what the baryonic component of that simulation gives. So in the center, of course, is the if you want LMC analog, so it's the central galaxy of that object, and it will have of order 10 to the 9 solar masses in the stars, which are shown in yellow. And then what we have done is to highlight the satellites that formed the stars, and those are the, you know, the star symbols over here. So by running cosmological hydrodynamical simulations on these halos with a model of star formation and feedback that we believe is reasonable, what we get is that LMC objects should bring some of the satellites with a stellar mass content that goes between a few times 10 to the 3 to, in this case, for this particular halo, 10 to the 7. That's the most massive companion over here. And also the circles show that many of the subhalos remain dark. And that is actually quite interesting, and I will talk a little bit more about that in a second. But so what we did is to explore a set of these objects. I think there were 5 or 6 in the sample, and then the pictures of those are down here. And you can already see an interesting variety on the companions or on the satellite population of these objects. For example, M11V has a couple of bright companions over here. This one, M11D as well, sort of interacting over here, and some other like M11C is a bit more quiet, etc. So let me be a bit more quantitative. And so what we did here, what Ethan did here, this is the stellar mass versus the Vmax of the subhalos. Okay, so the maximum circular velocity, this Vmax, is a proxy for halo mass, but for satellites it's better to use Vmax. So we use, but you should think about this quantity as halo mass if you want. And so this is the stellar component predicted by this hydro simulation. And for now, don't look at the gray symbols, just look at the colors. And so what we find is that for the most massive subhalos, there is some sort of relation between stellar mass and halo mass, but then the scatter becomes quite high for low mass subhalos. And that's exactly expected from theoretical arguments, but it's nice to see it happening in simulations where you are actually self-consistently following the physics. So the other interesting point in the simulations is that you can now quantify as a function of halo mass or circular velocity, maximum circular velocity, what number of these subhalos hosts a luminous satellite, or a satellite that has, or a subhalo that formed stars versus one that remained dark. And what you see is that if your Vmax is about sort of 20 kilometers per second, every subhalo will host a luminous satellite. By luminous, I mean that it managed to form a few stars, not that it's bright, but at least it formed stars. But then that fraction goes very quickly to 0 in the range between 5 and 20. And this is a success of the model, because this is exactly what we need to create this bending in the sort of the abundance matching, if we believe that cold dark matter and the number of substructure that cold dark matter predicts is correct. So now what do we do with the ones that do manage to form stars? You can now construct satellite luminosity functions for centrals like the LMC. And this is the result. So this is the stellar mass of the satellites, and this is a cumulative number. So you should read this as any of these curves. The colored ones are our simulations. For example, if you stand here, it means that you should get about 4 satellites that are 10 to the 6 and above. Okay. So in color are our fire hosts. There are 5 of them here. And so what you can see is that there is reasonable spread on the companions. And in gray is the dwarfs in the Milky Way that we believe could be associated to the LMC. All right. So what we find is quite a nice agreement between the observational estimates, that would be the gray curve over here, for example, of course, the SMC, I said it was the most massive satellite of the LMC. Fornax and Carina, those are in discussion. They have some orbital properties that suggest that could be companions. And then a bunch of ultra-diffuse dwarfs. And depending on whether, because I said it's kind of complicated to reconstruct the membership because of the tidal disruption going on in the Milky Way, you can get these ones are the most safe ones, but also there are other candidates, okay? And so by comparing with the simulations, what we learn is the bright end looks decent. So in principle, Carina and Fornax could be members. And then the predictions is that the ultra-faint population is considerably more numerous than the numbers that we already have, or the members that we have already identified. So then what we take away is that there should be more ultra-faint dwarfs associated to the LMC that we have yet to assign membership to. And on the bright end, it looks like if, in order to get an SMC or an Fornax, our blue and red objects are among the most massive in our sample. So more massive infall mass for the LMC would make easier to fit the bright end of the luminosity function on the LMC. Now, what we are moving on now, so that was a paper published a few years ago. What we are studying is what happens to the environmental effects of these satellites in environments like the LMC. And so this is kind of a busy plot, but what we did was to divide all our satellites into mass bins, stellar mass bins. So this is our faintest, the ultra faint bin. This is the next one in between 10 to the 5 and 10 to the 6 solar masses. So we are getting into classical dwarfs towards here, and then intermediate between 10 to the 6 and 10 to the 7, and then the most massive ones. And what I want to show you is perhaps this bottom left panel that shows that if you take satellites with this mass, this is the cumulative star formation history, all right? So what you see is that they're finished forming stars anytime between 4 gigayears and almost 12 gigayears of age. And that is quite different from the star formation history of objects that have the same stellar mass, but they were forming stars in the field. You can see if these objects are in the field, they form stars all the way until redshift 0. So we interpret this as saying that the environment of the LMC might be quite efficient at actually quenching satellites of this particular mass. What happens? Why is this mass particular? Well, so if you go below that mass, so these satellites between 10 to the 4 and 10 to the 6, they are mostly affected by reionization. So the environment of the LMC is not that special. And so if you take a sample of centrals or satellites of the same mass, they are not so different. At this intermediate mass, it looks like where the LMC environment kicks in. And then if they are more massive, that this is satellites here on the right, bottom right, then the LMC environment is just not aggressive enough. And then the satellites continue to form stars. So they're star forming. It's a bit better shown perhaps here. This is the quenching time, where you should compare the red histogram to the black histogram. And so what you see is that the centrals, so this is dwarfs in the field, you find that they have this double peak. So they are either quenched very early or quenched very late. Basically, they're not quenched, they're still star forming. Whereas if you look at the satellites of LMC mass objects in exactly the same mass range than these centrals, you get a distribution. This would be the black histogram that is much wider. And in particular, these objects highlighted here in yellow are the ones that we are posing as environmentally quenched by the LMC. And this, of course, speaks of not only the mass of the satellites, but also the mass of the LMC itself, the halo mass of the LMC. And so the prediction, at least from fire simulation, is that these LMC objects should have a quite rich hot corona that is shown in this panel here on the right. And in particular, so the last column shows the phase space diagram of the gas, in particular the temperature vertical and in the horizontal is the density. So these components over here in each of the halos, this is low density gas that is quite hot, 10 to the 5 and above, is present in all of the halos, and it might be the one responsible for quenching these satellites via run pressure stripping, for example. So that is how much we have learned on the scale of the LMC, or at least what we have done on the local group. And I wanted to move a little bit outwards, going towards clusters. So let me show you for relative positioning. So this would be the local group. And the things that we'll be talking about are taking you much farther away. Of course, the local group is great, because you can observe these very faint objects, but they are very close by. So there is not enough volume to be explored. So now the strategy that you can take is to go and look farther away into, for example, the environments of clusters, because clusters concentrate a lot of these dwarf galaxies. And so we have Virgo, the Virgo cluster over here at 17 megaparsecs. We have Fornax. It's a bit smaller than Virgo, sort of a groupish of the 10 to the 13, towards the end of the 10 to the 13 mass range. And of course, Coma would be somewhere like way outside of this, with 100 megaparsecs or so. So sadly enough, we cannot really study ultra faint dwarfs in these environments because they're so far away that we cannot really see them. But you will see that we are instead doing things that are comparable. They are more massive, but they are equal low surface brightness objects. And so over here is a plot with the stellar mass versus the effective radius, so the size. And so what I will be talking about is this population of ultra-diffuse galaxies. So ultra-diffuse galaxies were first pointed out long time ago in the 80s, but now surveyed a bit more systematically with Peter van Dokkum in Coma after 2015. Okay, so this is the reference over here. And so these red dots, red squares over here is showing you UDGs in the Coma cluster. And there has been, of course, many more seen in other systems like Virgo or nearby clusters like Fornax as well. So this population tends to be between, a bit more massive than ultra faint. So they peak about 10 to the 8 solar masses, but their sizes are a couple of kiloparsecs. So that is, the idea is the mass of a dwarf galaxy, but the size of a much more massive galaxy, almost like the Milky Way. So the fact that they are very extended gave to the idea that these things were failed Milky Way galaxies. So galaxies that were destined to be like the Milky Way, but then they truncated the star formation and then they didn't form enough stars. So the question is, how do they form? How do you form things that are so extended? So a bit historically, two years later, there was the idea that these UDGs tend to have a lot of globular clusters. And this is showing pictures from two works from Van Dokkum 2017 and from Peng and Lim in 2016. And so this is the UDG, and you see here circled all the globular cluster candidates. So of course, if you now compute the specific frequency of globular clusters, so this related to how much of the mass of stars is in these clusters compared to how much is in the galaxy, what you get is that these objects get specific frequencies that are highlighted here in color, well above normal dwarf galaxies. So this is the magnitude of the galaxy in this specific frequency. So then this sort of added to the lore of, these are Milky Way failed galaxies. This happens, so the number of globular clusters scales quite nicely with halo mass. So then that would give you something like a very high specific frequency. With time going by, we are now believing that there are more ways to form. Yeah, exactly. So this is what I wanted to maybe show. So the mass of globular clusters scales with the halo mass. So if you have a UDG that has a lot of globular clusters, you can make the connection that the globular clusters indicate a halo mass of 10 to the 12, but then the stellar mass is very small, right? So failed Milky Way galaxies. We now know that there are many more ways of creating this. UDGs, at least theoretically. But then that would be forming these UDGs in dwarf halos. And if you allow for these UDGs to form in dwarf halos, then there has been many ideas of how you can create them, either by spin, so your halo has a larger spin, so then your gas has a very large extension, or by other methods that are more related to the environment, like tidal heating or tidal disruption, for example. And also feedback can create, by this breeding mode, can create things that are very low surface brightness. But the question is, how do we now use observations to constrain any of these theoretical models? So the first step is to stop looking at individual objects, but try to compile a sample more complete of UDGs. And this is what Sang-Soon Lim and Eric Peng, we collaborated in 2018, and we did this for UDGs in Coma, a sample of 48 ultra-diffuse galaxies in Coma. And now you can identify in these HST images their globular clusters, and then what you find is that the specific frequency as a function of the magnitude shows a large dispersion. So the UDGs are shown here in red symbols. So it's true, many of them have very high specific frequencies, but also many of them have zero or even very close to zero or none at all. So this already hints to the idea that more than one process is needed to explain these ultra-diffuse galaxies. And now, using this relationship between the number of globular or the mass in globular clusters and the halo mass, you can convert this into a halo mass constraint. This is the horizontal line over here, horizontal axis. Then the vertical axis is stellar mass. So we are back to this abundance matching plot. And what we find is that the UDGs populate a wide range of halo mass, not quite so massive as 10 to the 12, but close. Some of them are quite close to very massive halos, but also some of them are very low mass in dark matter. So consensus is being kind of drawn that there should be more than one mechanism to form these UDG galaxies. How can we learn more about the dark matter content? Is by using globular clusters, but not only the numbers, but also the kinematics. Okay, so this is showing one particular UDG, the DF2, that is extreme object, also by the Van Dokkum group, that shows that you can see highlighted here the globular clusters for which they obtain a spectra, and they found a very low velocity dispersion, 8.4. And that can be accounted for only by the stars, which means DF2 is consistent with being completely dark matter free. And that's not the only one in the same sort of system, that is this NGC 1052. There is another second UDG galaxy, DF2, that also shows very low velocity dispersions. So then we have kind of the data is all over the place. Some of them have a lot of globular clusters, which implies very high mass, and some other ones shows no dark matter at all. So this is also showing work that we did with Elisa Tolova using Keck, showing UDGs in Virgo. So these three candidates are highlighted here in the boxes. And we also found globular clusters. They are the red ones for which we could confirm membership. And you can constrain, again, the velocity dispersion. You can transform into circular velocity. And so our work is these red symbols, and it shows that, the globular clusters that we find are too concentrated, so that the inner regions are degenerate between a 10 to the 11 and a 10 to the 12 halo mass. But some of them are kind of very low, and this would be VLSBD. So let me go back to the figure and show you. This is the guy, and you can see if you squint that is quite elongated, and here in the blow up you see that the globular clusters is also following that elongation that you see in the stars. So this is a hint that VLSBD is undergoing tidal disruption, something that I want to go back to later. But so the idea is then that there is a large diversity or dispersion in the properties of these UDGs. So what do we do from the theoretical side? We decided to look at this in these big volume simulations. This is the work that follows will be showing Illustris and TNG 100. work. So what we did is to select halos like Virgo cluster in illustrious TNG. So this is a picture of 9 of them, but we used 14 in our paper. And we studied the satellite population of these galaxy clusters. They are like Virgo. So we wanted to compare with the UDGs in Virgo. And so after some modeling of the structure for the satellites, what we find is so that if we put the satellite population of these clusters is stellar mass, and this is the 1D velocity dispersion. In gray, you have the whole population. Highlighted in color over here is the UDG sample. And so what we find is that there is a wide dispersion on velocity dispersion predicted in the simulations for the UDGs. And this dispersion correlates nicely with the tidal stripping. So you can see over here, they are colored by the amount of mass that has been retained. So what you do is you check the mass at infall, and then you check the mass at redshift 0, and you take the ratio. And so you see that if you had a UDG that didn't lose a lot of mass, then you just sit here in the upper end of this relation, and then the more tidal stripping goes on, the more you sink towards the lower end. So what we also found is that this population actually is formed of two things. One of them is just normal dwarf galaxies in the field that happen to be extended and that didn't lose any mass, and that's the upper end. And as you get to the blue ones were galaxies that were not UDGs at the beginning. They were more massive, like almost Milky Way-like, and they had been tidally disrupted. And the losing of mass not only changed their luminosity and their sigma, but they also made them very low surface brightness. And those are the ones that are located over here. So you see that the observations of UDGs, that are these purple symbols, kind of span nicely the range of values that we find. So that would say that VLSBD, for example, remember the one that was elongated in Virgo is over here, and it fits very nicely with our population of tidally disrupted UDGs, shown here in blue. And things like DF44, that is one of the first ones that was discovered that had many globular clusters, is consistent with being the UDGs that were UDGs in the field and thus were stripped off within the cluster environments. And then we were claiming that objects as extreme as DF2 and DF4 that had no dark matter could maybe be extreme case of tidal disruption, okay? But it's clear from these tidal tracks that if you have a core, it's more easy to explain these very low velocity dispersions. The interesting point about this is that this gives us some predictions. This dual mechanism for formation of UDGs makes strong predictions on the radial distribution of these UDGs within the cluster, where the tidal UDGs will be populating mostly the inner parts of a cluster like Virgo or Coma or Fornax or any of those. And then the born UDGs will be kind of distributed, more shallow distribution, and definitely populating the outskirts of the galaxy clusters. And this also, of course, correlates with the infall times. So you see over here, our population of tidal UDGs that is shown in this light blue have infall times that are typically much earlier than the born UDGs that fell into the cluster later on, shown here by this dark blue distribution. And that gives you predictions on, the quenching times and, for example, that you could, in principle, validate once we get better spectra of these objects. But of course, the question is, can we do any better? And one of the things that we can improve right now is to make a more fair comparison between observations and simulations. What I was showing before was all based on particle from the simulations, right? So directly taking whatever mass is within whatever radius. But that's not really how the observers are doing things. And the observers are doing this by studying globular clusters. The issue is globular clusters are not resolved in simulations like illustrious because they are too low mass. So what we did is to tag globular clusters into illustrious and TNG. So you see over here the result of the tagging. So the globular clusters are now dark matter particles that are selected to have the right orbits, like globular clusters. And we can discuss more about the method later. But this is the end result. This is one of our objects in Illustrators. So in gray, you see the stellar distribution. And if you squint, you can see these red and blue dots are our predictions for globular clusters. Of course, they cluster towards the galaxies, as they should, but also there is this population of orphans or at least intragalactic globular clusters that builds in with the method. The way we do this is for each of our clusters, we identify any satellite that falls in. And so before they fall in, we populate each galaxy with globular clusters. And then we just follow self-consistently the orbits of those particles. And so how is the dark matter inferred in the observations is using a spherical Jeans equation. This is the best way we can do for now. Spherical Jeans equation will relate the distribution, this is the radial distribution and the velocity dispersion of a tracer. This is also the orbits of the tracer, in this case, the globular clusters, to the general or the total potential of the object. So now the idea is the potential is dominated by the dark matter. Of course, the stars also contribute, but it's a minor contribution. Most of the potential is coming from the dark matter halo in the dwarf galaxy because of how cold dark matter works. And then by constraining the distribution and velocity dispersion of, or by measuring the distribution and velocity dispersion of the globular clusters, we can say something about that total potential. So then there are simplifications of this formalism. For example, this one is showing the Wolf et al. 2010, that this is mostly what the observers use to constrain the dark matter of these objects. And it basically says that the mass within the half number radius is a function, is some sort of constant. It depends on the velocity dispersion and the one dimension and the size or the half mass radius of that tracer. So then what we did is to use our globular clusters painted in Illustrators to study how well this formalism recovers the dark matter in dwarf galaxies. And this is work led by my student, Jess Doppel. So I'm really going to a very short summary of her work. It's a fantastic work, very technical, that I do invite you to look at if you work with these things. But so what Jess did is to study how well we can recover the dark matter mass in these cases. And she did this using different ways of estimated sigma, or the velocity dispersion of the tracers. And the thing is, you know, for massive galaxies, Milky Way and above, there are many globular clusters. So the methods, so we know that Jeans mass kind of goes well. But the issue with globular clusters in dwarf galaxies is that they don't have many. They have typically 10 or less. So now the question is how well you can recover the dark matter content of a galaxy with only 10 tracers. And so what Jess found is that depending on the method, you can do quite well. So in the upper panel, you can see the results of comparing the mass that you would calculate using the Wolf formula to the true mass, the one really in the simulation. And you find that with less than 10 tracers, you tend to underestimate the velocity dispersion. And these two curves show two different ways of estimated sigma. One is the simple RMS, and the other one is the byweight that is used in some of these, for example, the DF2 paper. And below here is using the MCMC method that is actually preferred by observers nowadays, especially if you have less than 10 globular clusters, and it shows you that your choice of a prior matters. So if you use, for example, a flat prior, that would be this purple line, you will tend overestimating your sigma, whereas if you use Jeffrey's prior, seems to be something that is a bit better for this kind of tracers, at least, right? That is in this tail color. So now we can actually do a more fair comparison, as I said, of what the observers measure and what we do in the simulations. This is the stellar mass, and this is the sigma, the velocity dispersion obtained using MCMC of globular clusters now in Illustrators. And so the symbols with error bars are observations. Again, our simulated dwarfs are in the right trend. What we find is that objects that deviate, so in the cyan line is the median sigma at a given stellar mass. So what you see is that as you deviate lower from this relation, so downwards, the symbols become darker. And if you go to the error bar, so the color bar over here, darker means less dark matter fraction. So again, this is confirming our previous results that you can form UDGs by tidal disruption. And the tidal disruption tends to lower the velocity dispersion quite a bit at a fixed stellar mass. And then the question remains, can we form things like DF2 and DF4 by tidal disruption? Now measured in a similar way than the observers, right? So now these sigma estimates are really fair compared to what the observers do. And so what we do, we find a few, you can see these dark symbols over here. They are close to some of the estimates for DF2, Emselem and Laporte 2019, for example. They're far away from the original estimate though, but at least some of them seem consistent with some of the estimates. So what we did is to select all the candidates in this stellar mass range that is consistent with DF2. And so what you can see here is the velocity dispersion coming from the globular clusters as a function of the infall mass of these objects. And so in the shaded area, what you see is the estimates for DF2. And we find that a few of our objects, these purple lines, these purple circles, overlap with these estimates, at least with the upper end of the estimates, which confirms that DF2 could be a dwarf that you formed by tidal disruption. And if that is the case, their infall mass could be a few times around 10 to the 11, okay? However, this is only partial success because it only reproduces the upper end of the estimates, and we find no object that is as low as the initial estimates by Van Dokkum. So if that is the case, it might be that we have a core in those objects, okay? So now for this, we will need better data, better observations. So I think I'm 32 seconds above my 45 minutes. So I will actually leave you with a summary of all the points that I presented.
Thank you very much, Laura. Next week, we'll be having a seminar on gravitational waves, and see you then. Now we go to the breakout rooms.